Our formal talk to go. Sometimes towards the end of the conference, you wish you had got to the end, but this is a conference I wish would keep going. I think it's been great. Our last speaker is Professor Bernard Burke, now retired MIT, but retired with very little change in the level of activity as far as I can see, and I'm on the other end of the world, and I still see Bernie all over the place. So very active. He has his degree from MIT, but spent a period of time, as you actually heard in the discussion this morning, at the Department of Terrestrial Magnetism in Washington, then returned as a professor at MIT. Has been a member of the radio astronomy community, certainly for more than the length of my career, and knows about almost everything happening in the field. So, Bernie, over to you.
I'll first address you because you made us all stay up late last night, and yet everybody was on time here this morning, and they seem to be staying awake. So, but just in case you can't stay awake, I'll give you a copy here. Well, when I was thinking of a topic, you have to do something radical. And sometimes doing something radical is sort of the anarchist point of view, tear something down. I've lived in a milieu of some very good people, very philosophical people, and I have to say that obviously Kuhn is in the background here. Popper pops up every now and then, and I had a lot of interaction day to day with Phil Morrison and with Vicky Weisskopf, and when he was at MIT with Steve Weinberg, and when I was at Caltech with Dick Feynman. And I have to say, none of them seem to have a high opinion of any of those people. And I think part of the reason is I was talking to one of our philosophy of science people in the Cambridge area, and he said, huh? Louder, okay. I was talking with one of the philosophy of science people in the Cambridge area, I don't remember who, fortunately, who said, well, you really don't have to know science to write about the philosophy of science. So be aware. Okay, I guess we can turn the lights down in case people want to. So here's the outline. Paradigm, as far as I can tell, is so carelessly used it does not mean much. Newton set the standard, and a paradigm, the notion of a paradigm is useful for big things, and Newton set the standard. Advances in science principally don't stem from theories of crisis, they stem from innovation and discovery. And you don't find much about innovation and discovery. In fact, radio astronomy is an example I'll give of how it's very hard to identify the paradigm change in the course of radio astronomy. Oh, there was lots of innovation and discovery. So let's start. I'm going to give an example of something that might be considered a paradigm change, but which I think I will prove is not a paradigm change. The discovery of pulsars. We know that Jocelyn Bell helped to build Tony Huish's telescope, and she was the first user of the telescope, and she indeed used it to good effect because she noticed a bit of scruff and followed it up, showed that it was. Am I not loud? She showed that the scruff was sidereal. Then Tony was her supervisor and joined in. Then Tony went on holiday, and it seemed that he took the pulsar with him. The story that Tony tells was that his array was indeed not built to discover pulsars. It was built to study interplanetary scintillations, and it was interplanetary scintillations that had removed the pulsar from view. They had to wait, and it came back. And the question arose, well, was it the men behind the velvet black curtain, or was it little green men? And but when they saw that there was a Doppler shift in the period, and it corresponded only to the Earth's motion, that eliminated the spooks. And it didn't have any other planetary motion, and so it looked like it was not the little green men either. So that was a good piece of science to pin it down. Now, there is a curious fact that Franco Pacini, in a sense, predicted the discovery. He said, if neutron stars were to exist, and if they had high magnetic field, and if they were rotating rapidly, they would generate a huge electromotive force, and that would stir up radiation from the surrounding plasma. You notice it's almost entirely in the subjunctive. It was published a month before the pulsar paper appeared. It was not referenced in the pulsar paper. Then after the pulsar paper did appear in Nature 1 month later, incidentally, Franco's paper was also in Nature. Then about 3 months later, Tommy Gold proposed his lighthouse model, essentially saying that part of what Franco said was right, but that he had the wrong idea, that it would be plasma at the poles that would generate a pulse as it rotated. The Cambridge group was stuck on the notion of vibrating white dwarfs. But when the Vela and Crab pulsars were discovered, then you had to decide, well, they showed that the period was much too high to be a vibrating white dwarf, but it still could be a vibrating neutron star. So it was established that pulsars probably were neutron stars, but is Tommy Gold's lighthouse model correct, or were they in fact vibrating? Now, I'm going to back up to the lovely paper we heard at the very beginning of the conference, where Srini gave us an outline of degenerate stars and the progress to a black hole. Baudin-Zwicky proposed that neutron stars might exist. Oppenheimer and Volkoff, and as we heard, it was a much longer story than that, but Oppenheimer and Volkoff certainly put it on solid ground. Now, it's very well to say that they might exist, but did they exist? And I know that nobody is willing to go out on a limb and say that they had to exist, because when I was still a youth, still at the Carnegie Institution of Washington, I heard Ed Salpeter give a lecture on hyperon stars. Were hyperon stars possible? Well, Hans Bethe was in the chair, and Hans had a simple question. He asked, Ed, do neutron stars exist? Now, Ed surely knew everything that could or might exist, and he basically, if I drew a cartoon, it would show fog coming out of it, rolling out of his mouth. He wasn't willing to say, yes, they must exist. So neutron stars were old hat, but they were hypothetical old hat. So I would say there's no sign that there's no any paradigm in the case of pulsars. They were generated by something that could exist. Good physics was behind it, good observations were behind it, and good interpretation was behind that. However, somehow the slide seems to have been lost, but it doesn't matter. I can tell you about it. There was another paper that was very important, where pulsars are vibrating neutron stars or rotating neutron stars. And it was red that provided the key information. because Rad observed the polarization of pulsars. And as the pulsar beam swept past, he saw that the polarization, the plane of polarization rotated. And that settled it. They were not vibrating neutron stars. They were indeed, Tommy Gould's lighthouse model was indeed correct. Well, that's not a paradigm. If anybody wants to maintain it's a paradigm, well, they can argue with me later. But what is a paradigm? And so I went to Kuhn. I hadn't read much Kuhn, by the way. I owned the book. I had skimmed it, but the more I read in the book, the less high my opinion was of Kuhn. Despite he was an MIT colleague, but that's okay. Well, Kuhn, after citing Ptolemy, Newton, Lavoisier, and Franklin, and Lyell, he writes, "These and many other works served for a time to define the legitimate problems and methods for succeeding generations of practitioners. They shared two essential characteristics. Their achievements were sufficiently unprecedented to attract an enduring group of adherents away from competing modes of scientific activity. And simultaneously, it was sufficiently open-ended to leave all sorts of problems for the redefined group of practitioners to resolve." Achievements of this, I've lost the bottom, but achievements that shared these two characteristics I shall call a paradigm. Now, I think there are some important words there. Sufficiently unprecedented. And the plural is used. It has to be a body of knowledge. And it has to really bring in people from competing modes of thought. Well, so to sum up his scheme, first we have pre-paradigm research. Then the paradigm is developed. Then normal science occurs, which is a form of puzzle solving. Already he's gone wrong. Astronomy is not puzzle forming. You see something that wasn't there or nobody else had observed. That's not solving a puzzle. That's discovery. And you're probably using an innovative instrument. That's not the way to solve a jigsaw puzzle. You don't use innovative instruments. So in the course of normal science, you notice a scientific anomaly. Well, maybe if you discover something new, you can call that an anomaly. I call it a discovery. So you make a paradigm shift or a modification, but these grow to sufficiently large proportions so there's a scientific crisis, and the scientific crisis is resolved by a paradigm change. Well, it's a very good scheme, and we all like to classify things, but classification has its limits because it can be a kind of Procrustean bed. You take the body that you want to fit into your classification and then you trim off the things that don't fit. And if there's enough data selection of that sort, we all know what happens. Well, let's have a closer look at a couple of paradigm changes that that Kuhn cites. First, over here, is chemistry, starting with Black and Glasgow. Lavoisier indeed deserves a huge amount of credit because he put chemistry on a much firmer basis and with rigorous criteria. In fact, I will show that he followed Newton's principles. Franklin did his bit also. Franklin in 1747 did beautiful experiments, very simple experiments that showed that the charge that people were moving around was a single fluid. Now, a lot happened, though, in the next years. First, Alessandro Volta showed that somehow chemistry was related to the flow of charge. Coulomb measured the inverse square forces. Ørsted. Now, Ørsted showed that a wire generates a magnetic field, a current through a wire. There's a charming story about that. It was done in a lecture demonstration. It's very seldom that a paradigm it's not a new paradigm, but it's probably a paradigm shift. I think you can call it that. He'd done an experiment. He'd passed a current through the wire before the lecture, and it hung a magnet over the wire. The magnet was like that, and the wire was like that. And then he left it to his assistant to set up the apparatus. Well, the assistant set up the apparatus, but instead of the magnet being perpendicular, he set it up parallel to the wire. And so Oersted said, yeah, now you students will see there's no effect between a current and a magnet. And he closed the switch. the needle shifted. One of the most delightful discoveries, I think. Then along came Gauss and Ampere and Faraday. And we don't, are these all new paradigms? I even hesitate to regard them as paradigm shifts. They just sort of came so fast that it must have dazzled the people working in electricity. And then, of course, along came Maxwell, and over mostly from 1860 to 65, but summarizing his great work of 1873. Maxwell tied it all together, and I think really did create a new paradigm. It's a little more complicated than that, because his mathematics, well, he was a very good mathematician, but his mathematics were very difficult to understand. In fact, he chose to use vector potentials. How many people enjoy using vector potentials? Not many. And it really wasn't until Hertz that in 1889 that the experiment showed that Maxwell really was right. And along the way, Heaviside used more modern mathematics and wrote Maxwell's equations in the form we know today. So there's a pretty soft development. I don't see any crisis here at all. Now, let's go on to the next. Well, this got a little scrambled, but the whole thing is close enough. In the meantime, there's a theory of heat. I would credit James Watt for being the first to really suspect that heat and energy were the same thing. Count Rumford, with his Cannon experiment, did more. Then we go through a list of people. James Joule, actually, he deserves a huge amount of credit. As I will say later, I'm skeptical about searches for young Einsteins. But here, Joule had to overcome a lot of obstacles because of the class system in England. Lord Kelvin, he wasn't Lord yet, but Kelvin was in the audience and didn't believe him when Joule described his paddle wheel experiment. That is, who could measure such a small temperature with such accuracy and build the machinery with such exquisite lack of friction that you could believe it? Furthermore, Joule had done some other beautiful experiments. He showed that chemical energy and electrical energy were equivalent. That's not as well known, but I think that was quite a startling achievement. So you have to give Joule a little bit of credit. I may run over time, but I have to tell you, how do you pronounce the name Joule? And there's a little ditty that goes something like this. Let me see if I can remember it. In lecture halls, where professors rule, they sing the praise of James P. Joule. But in chapel where the students howl, they sing the praise of James P. Joule. So landlord, fill the flowing bowl, and we'll toast the health of James P. Joule. Okay, so it goes down quite a list here of very famous people. And Maxwell over here is also over here because the theory of heat and the theory of atoms. Atoms are not generally accepted for a long time, but when Helmholtz did his experiments, and when Helmholtz did his experiments, he tied in conservation of energy and the existence of atoms. It was an amazing achievement at about the same time that Maxwell did his work. And Clausius did a great thing. Clausius invented the word entropy. And he unified things still more. And it finally, Boltzmann and Gibbs, of course, played their important roles. And so there you have what I would call the 19th century paradigm of physics. We've settled chemistry, we've settled atoms, and we've settled the question of heat and electromagnetism. Of course, then along came Planck. Whoops. Oh, now I've lost it. Oh, no. Then along came Planck. And now Planck actually unified things still further because he used Boltzmann statistics with the addition of the quantum hypothesis to tie together all of these things in a very powerful way. So you could almost include him in the course of the paradigm change. The curious thing is that there are beautiful experiments. The theory of Planck and the experiments of Hertz also contain the seeds of destruction of the old theory. Because a true revolution came along later, the quantum revolution. And you know what? Kuhn hardly mentions the quantum revolution. And that raised a question in my mind, whether did he? What? What? Louder. Well, I fear that Kuhn did not understand quantum mechanics, although it's unfair to. What?
It may be useful to use the podium. There is additional mic there. It may help.
This must be too faint. Well, I can use the podium. Okay. When I get my voice up, but then I get tired. Okay, so I'm not going to treat the quantum revolution. That really was a really new paradigm. Well, let's go on. I had trouble with Kuhn's use of the word theory. Now, what is a theory? And it's not what the public describes as, that's only a theory. No, a theory is something definite. When Newton put forth his theory of mechanics, and the theory of the solar system, he did not say, this is just a theory. He said, non fingo hypothesis. I do not make up hypotheses. Because a theory is a set of concepts that are correct within stated limits. Now, you won't always find that definition, but that really is what a good theory is. It is correct, but within limits. I once heard a lecture at MIT by Paul Dirac, and Vicky Weisskopf introduced him by saying it was appropriate that Dirac should give a lecture at MIT because we had a good electrical engineering department. And so Dirac began by saying, yes, he was trained as an electrical engineer. And electrical engineering taught him a very important lesson, that all of physics is just an approximation. Now, coming from Dirac, that's a pretty austere definition. We still have other useful categories below a theory. A theory is right within stated limits. But there are what I call a scenario. Other people use other words. A scenario is something that really has a lot to recommend it, and you really think it's right, but it's not proven in the full inductive sense. It has gaps that would help fill it in. And beyond the scenario, we have hypotheses, and below hypotheses, we have conjectures. And I'm not against any of those, but they're not theories. Well, Kuhn actually is doing what is trying to set up a Procrustean bed of forcing something to fit. And so it reminded me of a short story that Luis Emanuel Borges wrote. And in it, he has a parable about the great Chinese Encyclopedia. Everything was classified in the encyclopedia. The whole world was classified. Under animals, there were 10 categories. Animals that belong to the emperor was the first category. Fabulous and mythical animals, that was the second category, and we went down to 9 until we get to number 10, other animals. Well, I think you understand my point. That is, I'm sure that if you're going to stick to Kuhn, he needs to be readjusted and trimmed and twisted. So you can see I'm not a fan. But at least I got to read his book. Okay, let's look at 400 years of astronomy. Well, Copernicus, Brahe, and Kepler were the forerunners, but modern science began with Galileo. He introduced a tremendous invention when he started. He didn't invent the telescope, but he used the telescope to enormous effect. Following him came Huygens, who was also a major contributor to astronomy. And then came Newton. Now, there's a paradigm change. And, of course, in it he said, if I have seen farther than you, he was referring to his enemy, Thomas Hook, or Descartes, it is because I have stood on the shoulders of giants. Very high-class put-down. Well, after that came Bradley, who discovered aberration, a very important discovery, because in fact, even though Galileo saw the crescent phases of Venus as it went around the sun, it didn't necessarily fit the Copernican hypothesis. It fit the Tycho-Brahe hypothesis just as much, where the Earth was stationary and the rest of the system was going around us. But, of course, Galileo and Newton, they cut through that. They weren't going to have any such nonsensical thing when they knew something about physics. Well, there's quite a history, though. Herschel discovered Uranus, he made systematic star surveys. He looked at the structure of the Milky Way. Was that a paradigm change? No. He used very good telescopes and good skies, better than those in Europe, and enormously expanded our view of astronomy. Then came Huygens. Huygens took an innovation, spectroscopy, combined with photography, and he immediately changed the direction. Then we come to George Ellery Hale. Now, George Ellery Hale is somebody who also deserves a huge amount of credit, because he did two things. He founded the Astrophysical Journal, having done a lot of very good astrophysics on the sun himself. Officially, that introduced physics into astronomy in a big way. But the second thing he did is he recognized the need for large telescopes. When he was boy director of Yerkes, he built the largest telescope in the world. When he founded what was then the Mount Wilson Observatory, he built the largest telescope in the world, the 60-inch, followed by the next telescope, the 100-inch, the largest telescope in the world, followed by by the Palomar telescope, again the largest telescope in the world. So, and the curious thing is that Europe was almost 100 years before the Europeans began to build large telescopes, and that'd be an interesting question. Why? Okay. Whoop, I didn't. We got Annie Jump Cannon, who labored hard. I think that Kuhn would say that was just ordinary science, but it made a huge contribution to astronomy. Shapley determined our location in the Milky Way thanks to the discovery of Henrietta Leavitt about the period luminosity relation for Cap. And then there's the Kapteyn tragedy. Kapteyn was a great astronomer, and I give him credit for establishing a school, but it was a tragedy that he made such a blunder. I asked Oort about it, but Oort was very gentlemanly. And but Oort, along with Lindblad, they used physics to explain galactic structure. And so those were all very important discoveries. Were they paradigm changes? Well, now, of course, we come to another problem. Is special relativity a new paradigm? Well, I would say it was an improvement. It was a paradigm shift. But Newton is still, in fact, Newton's very smart. He wrote that the rate of change of momentum is proportional to the force applied. It was very shrewd. And now, general relativity, that's another problem. Yeah, you can make a case that general relativity really was a new paradigm, but it has a curious place in the history of science. Because when Hubble discovered the expanding universe, that was a discovery made by astronomical observations, by experiment. The theorists had nothing to do with it. They came thundering in because Einstein had a theory, general relativity, which in fact established the framework of cosmology as we know it today. But relativity was not an easy thing to understand. It was easy to derive the orbit of Mercury, but to try to interpret Friedmann's equations, for example, was not easy. So nobody went out on a limb, and Einstein himself had a sort of an 18th century view of a universe that's filled uniformly with stars. So the theorists were disconnected from the real world. So when the expanding universe came along, that really, together with general relativity, represented within cosmology a new paradigm. Curiously, it had no effect on physics as a whole. It did affect planetary dynamics. It has one practical application on Earth. And that one practical application on Earth is the GPS. The GPS does put in the GR corrections to get a little bit of extra accuracy. Now, I've treated, but the key element of the expanding universe was innovation. Large telescopes, spectroscopy, and here a huge amount of credit goes not only to Hubble, but to, what's his name? The mule skinner from, who worked his way up to being an astronomer. Humison, Milton Humison. Started as a mule skinner and ended up being a member of the National Academy of Sciences. So there is the, I think, a very interesting fact. And it's been true, I maintain, for all of our history, that cosmology is driven by observations and not driven by theory. And so I think, Roy, you're going to have to change your diagram a little bit to satisfy me. Okay. All right. Now we come to innovation and discovery. What does a young person need? The young person needs opportunity, means. You can't do it if you don't have the means to do it. You need to have the proper preparation. And you also have to have imagination. And which are nature and which are nurture is very hard to work out. But in opportunity and means is that marvelous fact that was drawn out by Professor Menon. It's striking how many of the outstanding people stem from a given school. In other words, the duty of the older person is to establish a school, maintain a school, and that is done so that you can bring young people in, and that helps to maintain the school. And Professor Menon told me a very nice statement. Was it by Bohr or who? But Rad uses the statement apparently too, and that is learned people attract learned people, and that's because they can recognize learned people. So, so the means are generally provided by a senior scientist or a school. There are exceptions, but they're special exceptions. That is, the low temperature laboratory at the Cavendish was established by Peter Kapitsa. And he had to build it up on his own, but he had the backing of the Cavendish behind him. He had experimental resources that he could draw on. And the preparation, of course, is a very funny question. I looked at the preparation of many people. My preparation was at MIT. I was a physicist, both undergraduate and graduate. I did my thesis in microwave spectroscopy. But it was an easy transition to go to a radio astronomy. Ed Purcell started off as an electrical engineer with a major in electrical power engineering. Of course, when he went to Harvard for graduate school, he became a physicist. Al Barrett, he also was an electrical power engineer at the same school as Purcell, Purdue. But he became a physicist at Columbia under Charlie Towns. Jim Moran, he also was an electrical power major to start with, and at MIT, he was an electrical engineer. He was not a physicist, but he did very good physics. Marshall Cohen. Marshall Cohen is another one of these electrical engineers, but we have to grant electrical engineers make very good physicists. So there's a curious thing here that people have come not from astronomy. I think none of these people, including myself, have ever taken a course in astronomy. Didn't hurt. Are there any paradigms? Well, Jansky started it all. That was a great discovery. And it was an innovative piece of equipment at the time. All you have to read is a series of 3 papers in 1931, 32, and 33 to recognize what great science it was. Grote-Reber mapped the radio sky. Hay discovered extraordinary emission from the sun. Van der Hulst predicted the 21-centimeter hydrogen line and started the Oort was able to get an experimental program underway. Interferometry at Cambridge and Sydney discovered much of the solar radio burst, but also interferometry discovered that there were exciting new objects called radio stars to start with, then discrete radio sources. Hay and Bolton discovered Cygnus A. And now there's a short, do I have time for another story? The story involves the director of Mount Stromlo, who later became Astronomer Royal. And I've been assured it was a story that's completely in character. Joe Pawsey was the first to try to see Cygnus A after they heard about the twinkling source of Cygnus. They turned this cliff interferometer toward the horizon. They didn't see it. So they were puzzled. They didn't see it, but it should have been there. So they went to Sir Richard Woolley and outlined the problem. And he had a very useful reaction. He said, "Stuff and nonsense, wouldn't waste my time on such rubbish." As Joe said, this was an enormous stimulus, it was a great encouragement. So the next night, John Bolton had the time, and he solved the spherical triangles correctly, and saw Cygnus A fringes. That Cygnus A rose from the sea. So there's lots more here. I'm not going to go through all of them. There's a lot of, not all of these are outstanding, but they're all very interesting. The discovery of the multi-phase interstellar medium. Rad did that. Development of molecular spectroscopy. Well, I'm not going to go through it all. We know it all. There's lots happened. It was a continually shifting paradigm in part of astronomy. And I would just say it was a lot of innovative equipment, innovative ideas, and creative use of discoveries. Okay, so my conclusion is most of these micro changes I call, if the answer to paradigm change, I say it's ridiculous. In some cases, okay, it's a paradigm shift, but that means you just tweak the machine just a little bit. However, I would say that the contents and phenomena of the universe, which is what we're trying to describe, it's far richer than we expected. So my conclusion is the paradigm should be used only for the big changes. The historical facts show that science is a process of innovation and discovery and usually progresses smoothly only rarely is there a genuine revolution, like quantum mechanics, which I will grant as a new paradigm. It's an excellent topic for party conversation, lubricated properly. Well, where are the opportunities? I've just been looking at pulsars, writing a review article, and I don't know much about pulsars, so it's a very useful exercise. They're supposed to be superfluid, superconducting, heavily magnetized degenerate objects. Well, superfluid, I think that's correct. But are they superconducting? I can't really find a persuasive argument that says they're superconducting. There are other questions, and related to that, why is the magnetic braking index not 3, as it should be, if the dipole radiation model is correct? And among other questions, how did the millisecond pulsars end up with a field of 10 to the 8 Gauss? I get 10 to the 4, that's a mistake. With a field of 10 to the 8 Gauss from 10 to the 12 Gauss if the things are supposed to be superconductors? And finally, how do you generate a solar luminosity in nanosecond pulses, which naively has to be generated within a few hundred meters? That's a real challenge. Okay, I only have one more thing to raise, and that's, we all know Rad's fondness for simple questions, and I think it was in the late 60s. There were several of us who were posed this problem by Rad. I take an electron. I drop it. Does it radiate? Well, the answer is yes. When I drop it, it's being accelerated, and it's radiating. However, if I am dropped at the same time as the electron, I just see an electron that's apparently stationary. Why should it radiate? You can't transform away a radiation field. You can change it, but you can't transform it to 0. There's a hint. At a meeting of general relativists at about the same time that Rad asked this question, this was discussed by much higher level people. John Wheeler was in the chair for the discussion. The discussion was inconclusive. And so John finally said, okay, I'll take a vote. And the vote was 50% said yes and 50% said no. Now, I'm going to ask that question here. When I drop the electron, does it radiate? How many say yes? Huh? I'm standing on the Earth, I'm holding an electron, and I drop it. Huh? How many, just raise your hand. How many say yes, it radiates? How many say no? There still are a few willing to do it. Well, I'll ask it a little differently. While I'm holding the electron, does it radiate? How many say yes? Rad says yes. I'm standing still. I'm holding an electron here in the palm of my hand. Does it radiate? I have another person who's willing to go on record. Well, it turns out, huh? What?
It's going out with the Earth.
Yeah, exactly. Now,
If you're in the station in the lab, you're outside the Earth,
now, let me describe the answer, because I was going to say the time's up, so goodbye. The answer is that about a year or two later, Bryce DeWitt solved the problem. The way I described it, the problem is very badly posed, because on the right-hand side of the field equation is the stress-energy tensor. And I have to describe the stress-energy tensor that's responsible for holding the electron there. So he solved a much better posed problem. We have a black hole, gravitational field around the black hole. We have an electron in orbit about the black hole. Now, you have to include not only the point mass of the electron, you have to also include in the stress-energy tensor the surrounding electric field, the energy in the surrounding electric field. And he showed that you get a major solution, which is the electron in orbit, but there's a little correction, and that's the radiation field. So The answer is it does radiate. If I was standing on the Earth holding the electron in the palm of my hand, I'm being accelerated as the Earth rotates. So, of course, it's going to radiate. It's not going to radiate much, you know, 1 cycle per day, but it will radiate. And so I think that that's enough is the answer that I just told you. Thank you. Huh? Yeah.
So that's a nice touch to end on some paradoxes. Questions?
So I'm just going to take issue with this. That can't possibly be right.
What?
That can't possibly be right. You've got an electron, a stationary electron in your rest frame, and it's losing energy. So where does the energy come from?
I did not say that it's in a stationary rest
No,
frame.
no.
I said I'm holding it in my hand, standing stationary on the surface of the Earth.
Yeah.
The Earth is rotating.
But in my local rest frame, if I'm standing next to you, you've got some energy.
You and I are both rotating.
Yeah,
Galileo established that.
Yeah, okay.
You'll lose.
No, you lose. I'll demonstrate it to you later over beer.
Okay, yes. I think it's helpful not to ask the question whether a given advance in science is a paradigm change, but ask what it's a paradigm change with respect to. I think there's a relativity of paradigmaticity, if I can use that word. So if I ask the question, for example, was the understanding of continental drift that was developed, we heard earlier today, developed in the 1960s, was that a paradigm shift? Now, to geophysicists it certainly was, but to physicists, fundamental, well, the Earth's a little planet, it's some little detail, it doesn't change the laws of nature. So what is a paradigm shift, I think, is relative to the subject that you're working in.
I'll grant that, but you better also be critical. I think in geophysics, it was a paradigm change, as far as geophysics is concerned. Just as the expanding universe was a paradigm change for cosmology.
Yeah.
But physics and chemistry did not.
Yeah. Well, I think this is helpful because there are lots of cases where somebody from outside goes into another area and points out something which to them is quite simple, but to the people working in the area is a complete revolution in their understanding of their little subject, you know, whether it's chemical engineering, whatever it is. And this happens again and again.
I think, right, you have to take it on a case-by-case basis.
Right.
I was going to use a quote from Alice in Wonderland. I didn't have it written down on the final slide, and with respect to paradigm and paradigm change. Somebody in Alice in Wonderland, and I'm not sure whether it was the red queen, the white queen, the caterpillar, or the Cheshire cat, but somebody said to Alice, when I use a word, it means exactly what I mean it to mean. No more, no less. So who was it? Marshall, you? Which one? I don't know. Yeah. Shirley promised that you'd know the answer. Yeah.
Okay. I think thanks again, Bernie, just while we have a moment in which everybody's agreeing. Just to conclude the meeting, we in principle have a slot left over. We've slipped most of the time, but we can spend another perhaps 20 minutes, maybe a half an hour. And what I had proposed was just to pick up a few topics where there was lively discussion or follow-up discussions occurring around here and continue those discussions. So the idea now is for everybody and hopefully as many of the young people who will participate as well to get involved in some discussions on a few topics which came up. And I primed a couple of people to trigger these. I thought I would start with Unikrishnan's question he put to you, not to have another discussion of whether the new theory of motion is correct or not, but his question he posed is, how does the idea of such a paradigm shift affect you? What do you feel about it? You want to lead them any further, or?
Well, I had presented a scenario with some empirical evidence to say that our present understanding of laws of motion, relativity, and dynamics is based on certain wrong premises, especially the invariant one-way velocity of light. That if that fact is empirically invalidated, so special theory of relativity has to go, and something else has to replace that as the basis of the theories of motion and as the basis of dynamics. And I propose that all relativistic effects as well as the laws of motion is completely determined by gravity of the entire matter in the universe. And I have sufficient evidence for that. Therefore, I demand a paradigm change. Now, we can discuss that.
So, that's some people. How do you react to that? How do you feel about that? Okay.
Well, it's a bit upsetting. Let me say first that we will all agree that there is a preferred frame in the universe. And so Einstein's notion that all co-moving frames are equal, that's wrong, because there is a preferred frame, and you know whether you're on it or not. You can tell how fast you're going relative to that frame. And in principle, everybody knows how old they are relative to the Big Bang. So all this business of the clocks, I think...
If you admit that much, give a little bit of rope, the entire thing
Well,
gets carried out.
I've gone part way. The rest of it is upsetting.
It's upsetting, but let's just look at what you just admitted. Let's say there is a universal synchronization possible, one frame. Then, of course, it's easy to prove that there is a universal, that is equal zeros of clocks in any moving frame, because you can locally synchronize clocks even in a moving frame. So this can be proved as a theorem. As soon as you say that, the first order part of the Lorentz transformation has to be just rejected. Okay, that's one thing. Second order part is part of all relativistic theories, including the old ether theory. So if you wanted to retain only the second order part, there was really no need to change the paradigm at that time. Okay, but related to that, yesterday you were saying that it's okay about the Machian results of Coriolis forces and so on, and inertia forces coming out of that. If you admit that much, then it is very easy to prove that the relativistic time dilation, length contraction also is from the same gravitational effects, because now you'll have to consider a relativistic theory of gravity, in the sense, if in a moving frame, if you start with a Newtonian potential, and if you transform to a moving frame with any relativistic attitude, you will pick up the second order terms. A vector potential becomes essential. And then time dilation and length contraction, all that will follow as a second order effects.
Okay, this is fine.
If you admit that much, whatever you are willing to admit, then I can prove that rest follows.
Okay, so the case has been made, and you made it in your lecture, and we don't have the time to debate the actual theory. I am interested in, from this group of people, knowing how they react to it. So what I was interested in Marshall's answer was just the first thing he said. He found it upsetting. Oh, that's the second. No.
I said that twice.
All right. So I'm not exploring at the moment what was upsetting, but you reacted as upsetting, and Ken is going to react.
I'm not really that upset because I've always looked at the things individually. But my problem is, what's the definitive test that I can actually do to distinguish between these two theories as an experimentalist?
Yeah.
And as a person that makes clocks for a living, I'm just wondering how accurate do I need the clock and how to set up the experiment.
So you see this as an opportunity to do another experiment, which would be my reaction, by the way. We better have some more. We've got lots of people wanting to talk. Can we get more microphones?
So my reaction would be the following, that what is needed is a critical examination of the empirical evidence that you have brought to bear in the formulation of your theory by the most skeptical person you can find who is out there to defend the existing theory of relativity, special and general, and if this critical evaluation by that person, if the examination of the empirical evidence survives, and there is no other explanation which is possible to be within the existing framework, then surely a case can be made for more experimentation to validate the one-way velocity of the speed of light, and so on and so forth. And that's how, at least, I would see a systematic examination of what is it that you propose.
Yeah, that is fine. I mean, that is sort of taken for granted that the experiment has to be scrutinized and it has to bear that test anyway. I mean, it has to pass that test. But I just want to remind you that the shift from ether theory to special relativity did not depend on any experimental evidence. I just want to be reminded of.
Fair enough.
Okay. But it was a very convenient theory, much simpler to deal with.
The reason I thought this was a topic worth discussing is behind your question. Yes, experimental verification would make all the difference. But if everybody is too upset or too risk-averse to spend the resources to do the experiment, it won't happen. This is an example of the way bias comes into science. Yeah, we know how it should be done, but is it being done?
Incidentally, I'm not so upset that I'm not so upset that I would want experimentation stopped. I'm all for experimentation.
Any other views people want to express, Bernie?
I don't like the word upset. That is, whenever one proposes something that is a radical change, I find it interesting, but I demand proof. And the more radical the suggestion, the more rigorous the proof should be demanded. So I'm asking
That's
about,
my view as well.
I'm going to ask about two classes of experiment. One, the WMAP results, of course, did not make use of this. And yet it sounded like something that should be measurable as another parameter in the WMAP concordance. Is it?
See, none of those cosmological results have any relevance to the test of these theories. Let me restate the result.
What's the tentative result?
Let me state what the theory is, what the paradigm is. It states that the laws of physics, like laws of motion, like the Newton's law, as well as all relativistic effects which we measure in the laboratory, time dilation, length contraction, and so on, they are all gravitational effects of the entire matter in the universe.
If I had a very good clock at the center of LIGO and at the end of the tunnel, one of these 10 to the minus 18 clocks,
yes,
would that show the effect?
It is already showing the effects.
Huh?
It is already showing the effects. It's what
It is already showing the
yesterday,
effect?
which I described as the muon lifetime, is also because of this gravitational effects. Okay.
The front row is monopolizing.
The detail I can discuss with you.
Okay.
These clocks are already showing these effects. And that is precisely why time dilation is not a symmetric effect, even though the relative velocities are symmetric in many of these experiments.
We'll have a couple more. Ray has the mic.
Okay, I'd like to respond to Ken's point, if it ain't broke, don't fix it. It is broke. So we've got this assumption right at the beginning of special relativity, there is no preferred rest frame, there is no preferred time, and yet we know from the Kobe and WMAP stuff there is a preferred rest frame, and there is a preferred time, so the onus is now on somebody to fix it. Now the somebody may be what you're suggesting, or it might mean going back and say, okay, well, when people said that, and when Laurent said that, he didn't really...
I'm the person that's always looked for a preferred frame and like to put things in certain places. I'm not convinced, and I haven't heard the real convincing evidence yet that I believe this.
When you first posed the question, I did think it was almost a satire on contemporary anti-intellectual styles. don't discuss the science. Just tell us what you feel about it. Okay. However, of course, your serious point is the worry about groupthink. Isn't it? That's your serious point. Now, it's inevitable that there will be resistance. I mean, people's private feelings, that's irrelevant if they're upset or disturbed, or, but it's clear that there will be resistance. And any idea that is sufficiently revolutionary will raise this. But it takes time. You know, you worried about reaching your 1,000 moons or whether it would take the 1,000. You know, you have to live with that. I mean, you just have to publicize your theory as much as you can, and then you need other people to agree with you or think it's worthwhile. And eventually there will accumulate this head of rigorous criticality which you desire. So, you know, this is the natural progress of science.
I have already realized this, and